Balancing oxidation-reduction equations. The half reaction method is a standard method of balancing redox reactions that occur in a water solution. Although there are circumstances in which it can be used when the reaction does not occur in water, these are generally only reactions in which there is no oxygen or hydrogen. This method is most useful when you are not given a complete listing of reactants and products, but rather only the particular species that are being oxidized and reduced. This method involves treating the oxidation and reduction as two separate processes, balancing these half reactions, and then combining them to attain the balanced equation for the overall reaction. This separation cannot occur in real life, since the oxidation of one atom, the loss of electrons, cannot occur without the reduction of another atom, the gain of electrons. Separating the two half reactions is usually easy if only the species being oxidized and reduced are given. Each half is then balanced according to a specific pattern, and the balanced half reactions are combined to eliminate the electrons and produce a balanced net equation. For the half reaction method, the first thing to do is to separate the oxidation from the reduction. This is usually done by assigning oxidation numbers to the atoms so that we can see what atom increases in oxidation number, that is, what atom is oxidized, and what atom decreases in oxidation number, that is, what atom is reduced. It may not be necessary to determine the oxidation numbers if it is obvious what the species are that are connected. For example, if dichromate is on one side and chromium 3+ on the other, with no other chromium mentioned, then it seems clear that those two species must be in the same half reaction, regardless of whether it is an oxidation or a reduction. Step 3 is to balance each of the half reactions separately. Balancing each half reaction means that we balance the atoms of each element and the charge. For each reaction, then, we do the following. Balance the elements other than hydrogen and oxygen. That is, balance the element that is oxidized or reduced. We balance the oxygen by adding water, which is where oxygen exists in a solution in water. The hydrogen is balanced by adding the hydrogen ion, H+. The charge is balanced by adding electrons. This part can be tricky because you add electrons to the side with the higher charge, either more positive, or positive as opposed to negative or neutral, or less negative. This will decrease the charge because you are adding negative charges. When you have finished balancing the two half reactions, electrons must be in the reactants in one, the reduction, and in the products in the other, the oxidation. If this is not true, then a mistake has been made. The half reactions are then multiplied by appropriate factors to make the number of electrons the same in the two half reactions. Then the half reactions are added, canceling out the electrons and as much else as we can. Usually only water and H+ can be canceled. Next, you should check to make sure that the number of atoms of each element is the same on both sides of the equation, and that the charge is the same on both sides. Once those are checked, the reaction we have is balanced. Let's look at an example. The reaction between the permanganate ion, MnO4-, and the oxalate ion, C2O4-2-. Note that only the species that are reacting are given here. Here are the oxidation numbers for the atoms that change. Manganese goes from +7 in MnO4- to +2 in Mn2+, a decrease of 5, so manganese is reduced. Carbon goes from +3 in oxalate to +4 in CO2, an increase of 1, so carbon is oxidized. Note that we can separate the two halves without assigning oxidation numbers. For the oxalate half reaction, we first need to balance the carbon atoms, since the oxalate has 2 carbon atoms and the carbon dioxide has only 1. So we add a coefficient of 2 to the CO2. Since we have 4 oxygen on each side, the oxygen is balanced, so we do not need to add water. Since there is no hydrogen in the reaction, the hydrogen is also balanced, and we do not need to add H+. This brings us to balancing the charge. One side has a charge of -2 and the other a charge of 0. We add enough electrons, 2, to the side with the higher charge, 0, to bring its charge down to -2. We follow the same pattern when writing the balanced reduction half reaction. The manganese is already balanced with 1 atom on each side of the reaction. There are 4 oxygen atoms in the reactants and none in the products. So to balance the oxygen, we need to add 4 water molecules in the products. There are now 8 hydrogen atoms in the products and none in the reactants. So to balance the hydrogen atoms, we add 8 H+ to the reactants. Next, we balance the charge. The total charge is +8 minus 1 equals +7 in the reactants and +2 in the products. So we add 5 electrons to the reactants to balance the charge. Now that the 2 half reactions are done, we evaluate them together. Note that 1 half reaction has the electrons on the left and 1 has them on the right. This must be the case. To make the number of electrons equal on the 2 sides, we find the lowest common multiple, 10, and get the number of electrons in both half reactions to that number. In this case, we multiply the first equation by 5 and the second by 2. Here are the multiplied reactions. When we add them together, we get this reaction. 10 electrons plus 16 H+, plus 2 MnO4- plus 5 C2O4 2- gives 2 Mn2+, plus 8 H2O, plus 10 CO2, plus 10 electrons. We eliminate what the 2 sides have in common. In this case, the only thing that appears on both sides of the reaction are the electrons. So they cancel out, leaving the reaction as shown. In every case, the electrons must cancel. A quick check of the atoms shows that they are balanced, and the charge is +16 minus 2 minus 10 equals +4 in the reactants and +4 in the products. So the reaction is balanced. Balancing in basic solution. The normal method of balancing by half reactions assumes that we have an acidic solution. We add H+ after all. Some reactions, however, occur in a basic solution. In a basic solution, hydrogen ions are not present in any significant amount, so to have them in the reaction is not reasonable. We could come up with a different way to balance reactions in basic solution using H2O and OH-, but that would be cumbersome and difficult. Instead, we first balance the reaction as if it occurred in acid, then convert to basic conditions after we have a balanced reaction. Converting to a basic solution is an exercise after the reaction has been balanced in acidic conditions. To convert to basic conditions, remember that we have lots of OH- present to react with any H+ that may be in the reaction. So we simply add enough OH- to react with all of the H+. This converts the H+ into H2O, one for each H+ that we had. To maintain the balanced nature of the reaction, we add the same amount of OH- to both sides of the reaction. If this produces water on both sides, we cancel the water from each side. Suppose the previous example had occurred in a basic solution. Up to this point, we would have done nothing different in producing a balanced equation in acid. Since we have 16H plus in the reactants, we add 16OH minus in the reactants and in the products to maintain the balanced equation. The 16H plus and 16OH minus in the reactants combine to make 16H2O in the reactants. 8 of these are canceled with the 8H2O in the products to give this reaction. Checking shows we have 16 hydrogen, 2 manganese, 10 carbon, and 36 oxygen on each side, and that we have a total charge of -12 in both the reactants and the products. So we have a balanced reaction in a basic condition.